Okay, so ideally when we have these differences between distributions, what we really would like is if there was very little overlap between these two distributions. The null distribution and the real one that we don't know anything about. It'd be nice if there was very little overlap. But in real life, there's usually a lot of overlap, right? The real world is noisy, and the real sample, the real population might be very, very different. Sorry. So the real population might be very similar. Sorry, I think I said different before. Might be very similar to the null population, right? And if that's the case, there's some overlap between their distributions, right? There's some chance that we might get a score over here, and it could be part of the real population or part of the null population, right? Okay, so if this is the case, then we need to understand these conditional probabilities in a new way, okay? So get ready. Here's the deal. Instead of writing real population, I'm going to say not null population, all right? Because we don't know what it is. It's just not the null population. Okay. I'm going to take this picture, this gray curve, and I'm going to draw it up here in two ways. I'm going to split it up into two parts. One part is going to be this blue part. This fail to reject region. Fail to reject, right? And that's that whole part. Here, I'm going to also draw this red part, but I'm going to draw it separately. I'm just going to draw it separated from each other so that you could see. Here, we have this little part, and that's red. And it's red because we've rejected, right? This is the case where we're actually wrong, right? But this is the case where we're actually right. Here we're wrong because we've rejected the null hypothesis, but we shouldn't have rejected it, right? Here we're correct because we failed to reject, and truly, we should not have rejected it. Now that's the case if the null hypothesis population is true. What happens in the case where it's not true? So the null hypothesis is false. Right? What happens here? Well, here I'm going to draw a sort of different looking set of pictures because I'm going to draw this curve. Right? I'm going to draw this curve now, but this curve split up. Okay? So here I'm going to split this curve up like this. So on this side of the line, okay, on this side of the line, I'm just going to draw this little section, right? And so I'm going to draw just this little section, right? And that part of it, I have failed to reject. Failed to reject, right? But that's actually wrong, right? So I'm going to color that in red because we should have rejected it, but we failed to reject it. On this other side, I'm going to draw the other part of this curve. So it's this part, right? And here I'm going to color that in blue because although we rejected, right? Although we rejected, we should have rejected it, right? Because here we've rejected the null hypothesis, right? We've rejected this null hypothesis, and you're right, you should have rejected it because you're in this new unknown, new population, right? So you should have rejected it, right? So let's look at the places where we're correct. We are correct here, right? And this is called a correct failure. here we're also correct. This is called a hit, right? Because we said, pew, we reject you, you're out of here, and we hit it on the nose. Now here, we are incorrect, and this is called a false alarm. Here we are also incorrect, and this is called a miss, right? It's a miss because we have failed to reject it. We failed to hit the target when we should have hit the target, right? We should have shot it. All right, so given that, let's see how the distributions and the box go together. Well, the false alarm is really that place. So remember, when the hypothesis is true, I'm going to draw it in black, right? The correct decision is going to be this whole section where we fail to reject, but that's okay. We're in this fail to reject zone, right? So you're good. You're good to go. But here, it's the other part of this, right? This part right here, right? And here, I'm going to say this is an error because we have rejected when we shouldn't have rejected. It's actually true, right? So this is our false alarm. Now, in the case of a correct decision, where you actually hit it on the nose, this means you rejected it, and it's good that you rejected it because actually a different population is true, not this null population. So that's going to be the area where you reject. So this side, so notice that all rejections go on the right side of this line, right? So reject, right? And you should have rejected because you're in a different population. You're not in the null population, right? Right? And so this is a good thing for you. You should have rejected. The other part of that, the other piece of that is down here. And here it's this little piece down here, this little piece right here. And here, it's incorrect because although you're part of a different population, not the null population, you didn't reject it, right? So you failed to reject. Fail to reject. So I want you to notice something here. All the fail to rejects are always on this side of the line, right? Because these are values that are less extreme than the mean, right? The rejection ones are all on this side of the line. I could have also drawn it two-tailed and also showing you this side, but I'm just showing you one-tailed. It's all outside of the line, on the outer boundaries of this line, right? Saying more extreme than the mean, more extreme than the hypothesized mean. This is less extreme than the hypothesized mean. So the hypothesized mean is somewhere here. Less extreme than that. The mean is here, more extreme than that. So relative to the hypothesized mean, okay? So that's how these four pictures fit together. So really, when you see those two distributions drawn, don't get confused. You already know it. You already know it. You just have to break it apart in slightly different ways. Okay, now let's go on to some examples. On the basis of results for a large, from a large sample of students from a university, a professor reports the mean height for my sample is not significantly below 6 feet. That means he did not reject, right? So this is fail to reject, right? Because if he said significantly, that would be rejecting the null, right? Which type of error would this professor worry about? Well, he failed to reject. That's important to know. What's the only error you can make if you failed to reject? Well, if you failed to reject, but you should have rejected, right? So failed to reject, but you should have rejected. When is that? The null hypothesis is false, right? What kind of error is that? That is a miss, right? And that's type 2 error, right? And remember, the error rates are given by alpha and beta, and so this is actually beta, so these are wrong. These are both correct rates, right, instead of the error rates. And this is nonsense. Having a non-significant results that all errors have been statistically avoided, that's never the case. You're damned if you do, damned if you don't. There's always a way you can make an error, right? Either type 1 or type 2. Example 2. A researcher worries about drawing incorrect conclusions. The researcher plans to select a sample of size 20 and to use the 0.01 level of significance. So here alpha is 0.01 in a two-tailed test of the null hypothesis. The critical t is it should be plus or minus because it's a two-tailed test, is plus or minus 2.86. So if he obtains a t of positive 2.8, which type of error would he be worried about and why? Well, you definitely know that he's not worried, you definitely know that he's not going to reject, right? So fail to reject. Let me write it in black. Fail to reject, right? Because this is less extreme than this. This should be plus or minus, right? This is less extreme, so he's going to fail to reject. The only error you could have when you fail to reject is if you fail to reject given the null hypothesis is false, right? And what kind of error is that? That's a miss, right? Or type, actually they don't write it type 2, they write it type numeral 2, Roman numeral 2. All right, what if he obtains a t of positive 2.869? Which type of error would he be worried about? Well, that's more extreme than this. So in this case, he would reject the null. Now, when is he wrong when he rejects? When he should have not rejected, right? Because the null hypothesis is actually true. What kind of error is that? That is a false alarm, or type 1 error, right? Example 3, what is the danger of the type 1 error? So this is a more conceptual question. The danger is mistakenly concluding that there is no significant difference between the obtained mean and the hypothetical population mean. Well, when you make a type 1 error, you have rejected the null, right? But null hypothesis is true, right? So mistakenly concluding that there's no significant difference, well, that's not true because you concluded that there's a significant difference. That's why you rejected the null, right? Mistakenly concluding that there is a significant difference between the obtained mean and the hypothetical population mean. Yes, that is true. That is true. Mistakenly concluding this, right? You mistakenly rejected the null. You said, oh, there's a significant difference, but you shouldn't have done that. Mistakenly being alarmed about a hypothesis when we should be calm. That's just nonsense. Mistakenly calculating the wrong test score. Remember, these errors are not errors that you can actually avoid. These are not errors because we were sloppy. These are errors that are made because we don't know the real nature of the world. So this is actually not what we're talking about when we're talking about type 1 or 2 errors. Mistakenly choosing the wrong population standard deviation to calculate standard error. That's not it either. These two are just regular old mistakes or errors in calculation. They're not type 1 and 2 errors of hypothesis testing.